Intel. Yeah. So I am part of Intel's team of Zephyr contributors. So yeah, I've been interning with them for a couple of years, and I've just recently joined full time. I also have a bachelor's and master's in computer science from UT Dallas, crushing comets, Burnham comets, Go comets, TMOC, whatever, etc. And I have no connection with Lauren Murphy, the American professional mixed martial artist fighter fighting out of Glendale, Arizona. I actually don't know that much about her, but apparently she has a 14-4 win-loss record, so she must be doing good. And yeah, so Lauren Murphy X64, that is my username on GitHub and Zephyr Slack, and that is my icon. So if you see that, that's me. You can correlate that icon with my face. So yeah. So this talk, it's 3 sections. We're gonna go over in the background. We're gonna talk about what machine learning is, the Internet of Things, all the basics, all the greatest hits. And we're going to talk about what TensorFlow is, TensorFlow Lite and TensorFlow Lite Micro, or TensorFlow Lite for microcontrollers. And then we're going to talk about how TensorFlow Lite Micro has been recently introduced as a Zephyr module. Then we're going to do a walkthrough / demonstration of our 2 Zephyr sample TensorFlow applications, and mostly focusing on the hello world. And then we're going to have a conclusion with some tips for developers, my heartfelt plea for contributors, and I will ask for your feedback, questions, comments, suggestions. So yeah, TensorFlow as a Zephyr module is very new. It came in for Zephyr 2.6. Of course, people have been building with TensorFlow on Zephyr before, but we're hoping to make it easier, more fun process, more Zephyr-centric, more Zephyr intuitive. So we welcome feedback from the community to help us towards that. So yeah, that's the outline of the talk, and I'm going to turn off my camera and we're really gonna get started. So to begin with this presentation, I won't force you to interact too much. Now, this isn't a college class where the professor will ask you a question every 5 minutes to make sure you're still alive, but we'll have some minimal audience participation. So I would like to check to see if, how many of you have used TensorFlow and have you used it with Zephyr? If you've used TensorFlow, put 1 in the chat. If you've used it with Zephyr, put 1 in the chat. So let's just, yeah, let's give a moment to see if anyone has used TensorFlow or used it with Zephyr. Oh, 0, thank you, love that. Oh, that's nice. People use TensorFlow, of course, I'm 0. No, we don't have any 1s. Well, I guess that's to be expected. Yeah, 0s. We have some Zephyr developers here, but just kind of see what TensorFlow is like. I plead the 5th. I love that. Love that. Okay. Well, yeah, so just to give you a background, guys, I think this may not be so much of a problem, but I am, like I said, I'm a Zephyr contributor, so I'm coming from the Zephyr side. I have a limited knowledge of TensorFlow. I did not study machine learning in college, unlike 99% of my classmates, but got some respect for it, and I think that on Zephyr it has some power, so look forward to enabling it. But looks like there are some of you that have some TensorFlow knowledge, so welcome. We love you, and but we will be kind of trying your patience a little bit while we explain some of the basics of machine learning and TensorFlow. So first, the background, and of course, this is the TensorFlow icon. You can see, kind of looks like a T from one angle, kind of looks like an F from another angle. That's the idea. So to kind of give you an idea, of course, machine learning is everywhere. Everyone, your brother, your mother, your dog, your dog's sons, baby, aunts, uncles, babysitter, etc. They all know machine learning, or they're interested in machine learning, and that's really cool. But yeah, what is machine learning? Well, very basic question. I'm sure a lot of you kind of already know the answer, but let's kind of go over it anyways. To kind of paraphrase an example from a technical talk at Google I/O, let's take rock, paper, scissors, the famous game. Now, many of you are programmers, I imagine, and if you were getting a number or an enum or, char or care, however you want to pronounce it, that indicated 2 of them, you get 1, the first person, that's what they played, R, P, or S, and the second one, the second character is RPRS, that indicates what the second person played. How much time would it take you to code who won rock, paper, scissors, put in minutes in the chat, or what language would you use? So I imagine Python, Bash, you could probably do it, JavaScript, a couple lines. Yeah, it's pretty simple, right? So, I mean, if we were playing code golf, I don't know if you know what that is. Code golf is where you try to get your program to fit in some constraints. So for example, length, you want the shortest program. You could probably do it in 31 characters, but that's all because you already know what the person played. It's in a computer readable format. And you can, from there, the rules can be expressed pretty simply. Scissor beats paper, or S beats P, paper beats rock, and rock beats scissors, And of course, if it's the same symbol, it's a tie and you got to redo it. So pretty simple set of rules for you to program. Take like 10 minutes, right? Maybe less, probably a lot less. Now imagine that I moved into your house, and every time you tried to install TensorFlow on your laptop or your machine, I threw it out the window. Or imagine you were living in the 70s and TensorFlow didn't exist, and you were tasked to recognize from images or a live video feed of two people playing rock, paper, scissors to recognize the gesture or recognize the object of their hand as a hand, and then recognize which hand signal it is. Scissors, rock, or paper. So that is considerably more difficult without, that human intellect, which is able to look at that and through some mysterious process, I'm not a neuroscientist, recognize it as one of these three symbols or not a symbol at all. So for the computer, it's a happy face when we have the input, but when we have this kind of an image, not such a happy face. So but our ancestors did get along before machine learning existed, right? We were able to do motion detection and recognizing blips on air radar, etc. So, when I say ancestors, I mean the 70s. So I guess not really for most of y'all, but for me, because I'm very young. But yeah, so machine learning, the difference between machine learning and traditional programming is that in traditional programming, you have to come up with that complex set of rules. You have to codify. I see someone commenting that Andy would do it in assembly. Yes, of course, assembly master. So yeah, so you have to come up with that complex set of rules. For recognizing a hand out of an image, that would be a very long program, and you would probably not get it right most of the time. Well, if you really tried, you could probably do it, but would it really be worth it? But yeah, so traditional programming, you have to come up with those rules, you put in the input data, and you get the answers out. But with machine learning, you have the answers already, some of the answers. So for example, you give it this database of 1,000 images, rock, paper, and scissors that have been labeled by human volunteers. And you give that to the computer and say, this is a rock, this is a paper, this is a scissors. It's kind of like, I guess, a child. You say that's a dog and that's another dog, right? So, etc. And the machine learning, the training process, it comes up with the rules codified in a model, and it can apply that to any future data to come up with new answers. And the accuracy, of course, will not be perfect, but it may get pretty close. So what's TensorFlow? Now, there are 20 other machine learning platforms in this world. You can check out Wikipedia for a comparison matrix, but this talk is about TensorFlow. I mean, everybody knows PyTorch, and maybe not everybody. I guess y'all said there were some people that didn't know anything about machine learning, but there are many, trust me, very many libraries. But TensorFlow is pretty popular because, of course, it's an open source software stack that is maintained by Google, and it's hosted on GitHub. So it's written in Python and C++, C/C++. And TensorFlow can also be used to refer to the end-to-end platform/ecosystem, which is to say, the tools, libraries, service partners, and vendors, etc., and the community. So it's pretty expansive. There's also the more specified TensorFlow Lite, which is for mobile devices or embedded devices that don't have significant resource constraints. So not the kind of devices that you would typically put Zephyr RTOS on. So then these would have like Android, or you could put Linux on them even. So even though these are smaller devices, and of course mobile, you put the entire Android operating system on there. So it can handle some stuff. I mean, my phone, it has 2 gigs of RAM. So That's pretty good. I'm sure the Pixel has like 16 gigs more than my laptop or something. My personal laptop, not my work laptop, though my work laptop, go Intel, no complaints. But yeah, it has APIs in several languages, including Python, C and C++, Java, JavaScript even, which surprised me, so you can do some processing on the client side in the browser. Go, Google's Go, I mean, I'm sure you've heard of that, etc. There's also third-party support for other languages like Haskell, I think, maybe, Julia, Swift, also, I'm not sure. But yeah, so many companies have actually already adopted both TensorFlow and TensorFlow Lite. So for those of you who don't know much about machine learning, it is no longer the thing of the future. It is the thing of now. Twitter and Spotify use it for their uncanny recommendations. For example, Twitter's ranked timeline, which is perfectly optimized to utterly waste your time. That's why I deleted my Twitter, but I should probably make it again so that I can retweet Zephyr IoT. Go retweet them. So. But Twitter's ranked timeline is using TensorFlow, and Spotify also uses TensorFlow to make its, excellent recommendations and, playlists, which allow it to continue to have dominance over Google's YouTube Music, which is, pretty surprising because Google's taken over the whole world. Google products also, of course, use TensorFlow. I think Gmail is one of their most notable products using TensorFlow. And of course, because so many companies are using TensorFlow in their products, Intel, ARM, and other hardware vendors and etc. have invested in optimizing their CPUs and GPUs to run TensorFlow applications, TensorFlow models, training, inference, etc. So, and you do need to do some optimization because this library, it does a lot of linear algebra, pretty complex math that GPUs do very well, but of course you want to be able to do it on a CPU too. If you have a CPU, you want to, maybe you can't afford to put a GPU in a certain product. Yeah, so both Intel and ARM are working on that, and they've actually done some great work on that. But TensorFlow is also used in cutting edge research in medicine and computer science, of course. Other fields, I think, logistics and supply chain is also a pretty good place for machine learning to kind of figure out how to make things more just in time. Well, maybe not now with coronavirus, but well, I'm sure there's something you could do about coronavirus too. But yeah, TensorFlow was released in 2015, I believe, by Google, and TensorFlow Lite sometime between 2017 and 2019. TensorFlow Lite Micro is a little bit more difficult to determine, but it's been around and there's been some serious consideration of it since at least 2018 or 2019. So that's TensorFlow. So machine learning on a microcontroller. Well, TensorFlow Lite Micro is an open source stack, same as TensorFlow and TensorFlow Lite, and it's written in C and C++ with a C++ only API, and it's for resource-constrained devices, the kind of devices you would run Zephyr RTOS on, which I'm assuming those are the kinds of devices that you all are interested in. So, but people have this common conception that machine learning is for the cloud. For you TensorFlow people in the chat, you may have more knowledge about this, but that seems to be the popular conception that you need to have these, CPUs and GPUs with a ton of computational resources running in this wildly expensive Amazon box or some lockdown, oil-cooled data center with this huge, massively complex data pipeline feeding into it and doing training and doing inference and etc. Yeah, somewhere out there kind of gives you Terminator vibes, right? So, but machine learning on the edge does have some distinct advantages. It results in less data flow, which is less stress on the network and less computation in the cloud because there's less network use. And another result is less power use, well, in terms of battery. But to give you an example to kind of explain it, let's say that you wanted to do predictive maintenance. Now, you don't need machine learning to do predictive maintenance, of course. I mean, as far as I understand. But if you wanted to apply machine learning to predictive maintenance or some other factory control or monitoring, you would probably have these devices, these tiny little devices, stuck somewhere to a wall, and it wouldn't be really efficient to hook up power sources to all of these. You'd be putting cables everywhere. It's a huge OSHA violation. It's just not fun. So you would want to have these little battery-powered devices, and they'd be collecting tons of data every day in, whatever resolution you want. But whenever you use Bluetooth to transmit it from the, I don't know if I can say that, there's a different word for it. From these followers back to the leader device, that's the uplink back to the cloud, you want to collect that data, but every time you use the Bluetooth or use the network radio some way, that consumes a lot of power, even, like I said, even with the low power Bluetooth. So that, of course, is not a desirable thing. But if you perform some minimal computation, that uses a lot less power, and you can filter out the data to be sent back to the server. And you can perform a lot of computation and do a lot of inference, like I said, directly on the device, and maybe even use the results directly on the device. Blink a light, for example. It's a red light. Something's wrong. We don't necessarily need to send it all the way back to Kalamazoo or whatever. So with that in mind, it's also a desire on the part of people to do these kinds of edge computation, edge machine learning, so that we don't send people's personal information in the cloud. Because, the more places your personal data is, the worse it is. Now, of course, I guess some people, paranoid people, myself included, you won't necessarily trust that someone isn't condensing your data and sending it somewhere, but it does increase consumer confidence if you're saying that you can keep their data on their device. So Echo can do all of its speech recognition on the device without sending back your strange search history to Amazon, which, I guess it might do that anyways, but in any case, yeah, so that's another concern for edge computing that they address. But to give you a more detailed example, this is an example borrowed from a technical talk by one of the leads of TensorFlow, technical leads of TensorFlow. His name is Pete Warden. He was speaking with some people that were trying to build, or they were building satellites using cell phone components, and it was a pretty good satellite. I imagine it was small, and it captured pictures in extremely high resolution at very high frame rates. The problem was that these satellites had a window of once every few hours to send a few hundred megabytes down to the base camp, or the base. I don't know what the technical term is, the military term, but the result, because they needed to capture all of that data, the result was that they would have low resolution images. And I imagine the same problem is for the Mars rover. They can only send back so much data at a time, right? So they won't send you these super high quality pictures of the entire surface of Mars. They'll send you pretty low resolution. So in that case, what can TensorFlow do for us in that case? Well, what we can do is we can use edge computing. We can use that TensorFlow inference on the device. Once you've trained the model to recognize clouds or blank expanses of ocean or the same kind of thing, airing an image, we can just throw away those images or send those images in extremely low resolution because there's no interesting features there. But if we can use TensorFlow to recognize an interesting feature, like a ship or, I don't know, a UFO landed somewhere, we can send very high resolution pictures of those interesting features. That would be optimization. So that's a good example. Now, as for TensorFlow Lite and TensorFlow for JS, which is TensorFlow in the client, on your browser, we can see that this edge computing has a lot of uses. There's a lot of case studies. I think someone's mic might be on. But there's a lot of case studies as to the uses, like, corporate case studies. But as for TensorFlow Lite Micro, I personally do not know that many case studies. TensorFlow doesn't have them published on their website. There appear to be a lot of research papers about TensorFlow Lite Micro, but there isn't really much, practical uses publicly out there. Now, this may be because there's a lot of people who are currently working on their killer apps for TensorFlow Lite Micro, and you may want to join in, but I guess we'll have to wait and see. But I do see from the examples that I explained to you that there's a lot of potential in this edge computing. If you can do it, if you can find an application for it, it would be very useful. But TensorFlow Lite Micro and other tiny ML or edge ML or whatever you want to call it, it has some limitations. In particular, TensorFlow Lite Micro has support for a limited set of platforms. You can see that list of platforms by following that link and going to their repository. Arduino, Cortex-M. There's a couple different things. I think one of them is called Blue Pill. I've never heard of that. Very interesting name. I should probably investigate. But there's also a support for a limited subset of the TensorFlow operations, because not all of these operations are very, they're kind of resource intensive. They're not very good to be adapted on a, resource constrained device. So this may constrain what you want to do with TensorFlow Lite Micro. In addition, there's a very low-level C++ API that requires manual memory management. And on top of that, there is no on-device training. So for those Python jocks that have a lot of experience with TensorFlow and you love doing it on your desktop and you can train it to recognize dogs out of images, that's not going to happen on your little tiny your little feather board. I think it's a Adafruit feather. That is not going to happen on there. Yeah. But in terms of the support for a limited set of platforms, you can port TensorFlow Lite Micro to a new platform yourself. For people that are desire to develop a board themselves, this may be what they do. Because the library is just pure arithmetic with very few dependencies on other modules or requirements. I think they only incorporate 3 libraries, one of which is I think all 3 of them are Google libraries maintained by Google. It's really not that difficult to add that support. You don't need OS support, but for the sake of your application, you may also desire to use TensorFlow Lite Micro on Zephyr. Now, if you've been attending the talks and if you've been reading our website, we talk a lot about the advantages that Zephyr RTOS has over bare metal or roll your own OS, or even the more kind of do-it-yourself, a little bit more intense, at least to me, coming from the Zephyr perspective, like FreeRTOS, Amazon FreeRTOS, which is cool. But yeah, we have some support for over 170 devices, which is more than any other RTOS, I believe. At least that's what website says. And we have great documentation and tooling like West and other tools. Love that. Love the SDK. We also have good community support participation, as well as industry and vendor collaboration. So Google, Facebook, there's a ton of people who are contributing their engineers, their resources, and their time. And Intel, including Intel. Don't forget about Intel. We, as Zephyr RTOS, can provide the support that TensorFlow Lite Micro needs, which includes, basically there's only 4 things it needs according to their README. Debug logging, which is just an output somewhere to a terminal or UART or something. The CMath library, C++11 compiler compatibility, and global variable initialization. We got that. So we also have other features like power management, logging, Bluetooth, etc. If you need it, we probably have it. All you have to do then is provide the application. So, killer app. So what does it mean that TensorFlow Lite Micro is now a Zephyr module as of Zephyr 2.6? Well, a Zephyr module is basically, there's some other uses for it, but a Zephyr module is a Zephyr library. It's a library that you can build into Zephyr. I'm sure there's other uses for it, but hardware abstraction layer. But yeah, you can build in TensorFlow Lite Micro as a library using the Zephyr build system. Before that, you had to use the TensorFlow-centric build. And I think you should try, if you're curious, to build one of the Zephyr samples in the TensorFlow tree. It's a little bit unintuitive for someone coming from the Zephyr perspective. They put a lot of work into making their build compatible with basically any platform. So it'll work for bare metal and it'll also work for Zephyr, but it's not, because they can't do it Zephyr-centric, it ends up being a little bit intuitive for the Zephyr users. So for example, it uses make files, which in the end calls CMake, which generates more make files. And yeah, but props to them for enabling it in the first place. But building it with Zephyr is a lot easier using Zephyr's CMake-based build system. All you have to do is set a configuration option using our kconfig configuration system to incorporate that module and write a very short CMake file. And you can use the TensorFlow Hello World sample to do that. You can model it off of that. So now that we're here, I'm going to do a short demonstration. Oh, and I also forgot, I think I will be able to make it through this demonstration, but Just as a side note, I don't know why I forgot, this is actually pretty serious. I live in Austin, Texas, and we are known for our power outages, I guess, now since the winter. Don't know why it's still going, but I had a power outage, 2-minute power outage at 12 today. Well, I guess it'll be 10 PST. And that kind of knocked out my internet for a good 5 minutes. So if that happens again, I will attempt to get back online with my phone data, just to let you know. But in any case, I think we are doing pretty good internet-wise so far. Now, let me just move this over here. We'll bring up. So can you see Visual Studio Code? You know, if I could get either something in the chat or, okay. Oh yeah, that's nice. I see those little thumbs up. That's really great. Thank you, thank you. Okay, so the first thing we're gonna start with is the Hello World example, but I guess we can kind of overview both of the Hello World and the Magic Wand examples. So first things first. You can see here, is this text big enough? Let me know if it's not, like put something in the chat because I may not, okay, I see some thumbs up. That's good. All right, so this is the Zephyr tree. You may already, and I think you probably are very, very familiar with the Zephyr tree. Now, recently, under samples and in modules, we have NanoPB as well. We have TensorFlow. Ignore whatever this is. I do not know what that is. Does not matter. But under TensorFlow, we have the Hello World and Magic Wand, so you can find them there. But for the purposes of our demonstration, I have reopened these folders here. I find this to be kind of a best practice when it comes to working in Visual Studio Code. If you open it in here, you can kind of, if you have your custom, CMake set up with VS Code, you can kind of get it to give you a little bit of prediction in terms of, and give you a little bit of information. So, for example, like, well, it's not working right now. It gives you some data like that. Anyways, that's relevant to the example. But yeah, you can see here, I've opened it as a separate folder. So that's the Hello World sample. Now let's talk about what these two samples do. The Hello World sample, you can see in the README as well, it replicates a sine wave. If you remember high school geometry, or I guess also college calculus or high school calculus, depending on where you were. Basically, you give it an x value that ranges from 0 to 2 pi, and it kind of gives you a wave, in radians. It goes up to the max value, and then it slips back down, it goes back up. So you remember, it's a wave, right? So the model, instead of mathematically calculating the sine of x, it predicts it based on some input data that we gave it when we trained the model. So it predicts the sine values in radians. The Magic Wand example, unlike the Hello World example, actually uses hardware. It uses accelerometer data to recognize gestures when you move the board around, to recognize them as wing, a slope, or a ring, right? So those are the two examples. But first, we'll talk about the Hello World. So to get the Hello World to work, we're gonna, okay. Let's get another bash one going, go into Hello World. That's really strange how it has a different icon, and we'll call it magic. So here we are in Hello World. You can see we have a build folder here. I'm going to delete that so that we can start from scratch. A lot of the times it is a good idea to start from scratch when you're rebuilding, if you can do that. I mean, I'm on a NUC, so Intel NUC, go Intel NUC. I can basically do whatever I want, run Twister on here with basically no repercussions. Well, maybe not Twister. Twister kind of stresses my CPU out sometimes. But yeah, so we're gonna rebuild it, and following the README, well, you can't really, this will generate the command, but I'll just show you here. Let's build, give it the board. We're gonna run it on QEMU x86 emulation. Now, because this sample uses no hardware, it just generates the x values from 0 to 2 pi repeatedly. We could build this for any board, but we're gonna run it on the emulator just so you can see how it works. So build it. generates the build system. Don't worry about that config. I feel like I've seen that every time. And you can see here, it generates the X value and puts out the Y value. Now, the original TensorFlow sample would just infinitely repeat these. For the sake of our CI, we stop it after about 50. But yeah, that's the hello world example running. So like I said, this will run on basically any board because again, it doesn't use hardware. So feel free to try this out on any board. If you run into any issues, you know, ping me, put something, but this should work on basically any board. Okay, so that's the hello world demonstration. Now let's talk about what makes this all possible. We'll first talk about the two files that you need in your Zephyr app and what you would need to do in terms of enabling or just to explain to you what's in there in case it's a little confusing. So project.conf, of course, you need this config option. This brings in the library. And of course, when you want to bring in the library, you need to make sure that West is downloading it into the modules folder. So this is your Zephyr folder. I call it Zephyr external. I think most people call it something else, but yeah, I call it Zephyr external. So in your modules, when you run West update, you need to make sure that it's downloading the TensorFlow Zephyr module. And you can see here, it's basically a copy of the upstream TensorFlow library, except that we've made some of the patched files, static files, which are generated by their complex make file system. Instead of attempting to replicate that, we've just brought in their third-party dependencies. And we have a little module.yaml here. So this is just for the people who are interested in contributing, which I would definitely welcome. Okay, so yeah, you need TensorFlow Lite Micro, you need C++, and you need some kind of libc. You need something with the lib. So these are the recommendations. All right, I can't see the screen share. Is it a problem at my end? Can other people see the screen share? Okay, it seems other people can.
I can see it, Lauren.
Oh, hi, Amber. Yeah, okay. It looks like it's just you then, Leonidas. I'm sorry. Maybe if you disconnect and reconnect, it'll work again.
The screen share will be captured in the recording too, so you can catch it later.
Oh, okay. Now we can. That's good. All right. Awesome. So let's continue. Right. So the CMake file, this is all pretty standard Zephyr fare. I won't really re-explain to you because I feel like that'd be boring. But for people who are curious and they see this in the app, you may not need this for your own TensorFlow app. If you don't use constructors, if you don't use local static initialization, then let me show you what local static initialization looks like for people who are unaware. Split left, and we'll look into the source, and I believe on the make functions, it should be okay. This is a static, right? So on its face, there's nothing wrong with using a static in Zephyr. But the thing is that when you bring in the static, the default normal reaction for Zephyr is to attempt to compile it with the thread safe statics. This is a pretty complex thing. You can Google it for more details, but it tries to bring in the C++ ABI for thread safe statics. But Zephyr doesn't support that, so the build will crash if you try to use local static initialization. The samples use it. The samples use this local static initialization. The library does not, and you don't need to use this in your app. But if you do, then you would need to bring this in here. You need to bring that, copy these lines, because otherwise you need to turn off thread safe statics, and you need to make sure that you aren't using static constructors that need to be thread safe, because when you turn this off, there's also no protection. But the constructors that they use in the sample aren't requiring that. So anyways, we turn it off in C++ compiler. So just these two files, project.conf and CMake list, will enable you to build a TensorFlow app. Pretty great compared to all the digging around in the file tree you might need to do with TensorFlow. You know, nothing but respect for them, but this is more of a Zephyr-centric model. So, all right, let's take a look at how the structure of the Hello World app kind of works. Now, a lot of this is kind of designed to be compatible with other frameworks and other platforms. For example, Arduino kind of requires this setup and loop thing. And like they talk about here, main is kind of normal. I really, there may be some reason for why you don't want your main function to be named main, but in Zephyr, it's also main. But you don't necessarily need to have this setup and loop, unless you're going to be targeting Arduino or something like that, which even then, I think Zephyr will handle that for you. You don't necessarily need to have setup and loop. But anyways, yeah. So that's the main, but we're going to see what's in the setup and what's in the loop. Okay, so in the setup, there's some stuff here. This is, like it says, it's just for compatibility with Arduino. I don't really know if this is completely necessary, but the namespace portion, I mean. But yeah, so we'll skip over that, but we'll talk about setup. And like they said, this is only for Arduino compatibility. The purpose of the setup function is, and you need to do this regardless of whether you call it setup or not, you need to set up this, TensorFlow, what TensorFlow needs to operate, which includes an error reporter so it can print to the screen. This is the output of the error reporter. You need to get the model out of the model data, which I'll show you in a second, which, it's in the form of a C array, and you'll see what that looks like. And I'll talk about how to get from a TensorFlow Lite model into a C array. And you need to, check the version, etc. Bring in the operations you need. For the purpose of this example, they bring in all the operations, but as I understand, this kind of bloats the size of the application. So I'll compare it to the Magic Wand sample, which is a little more optimized. If you look in the Magic Wand sample, you'll see here that it brings in exactly the 5 operations that it needs. So for you, this may be what you need. You may need just these operations. So that's another part. And you need to build the interpreter, which is what actually uses the model to interpret the input and, et cetera, et cetera. And your input goes into this pointer. Your output will be in this place. So you get it out and inference count, blah, 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 et cetera. So that's the setup. And it's not in here, but in the setup function, you will also want to set up hardware. In the case of the Magic Wand sample, we are using the ADXL 345 accelerometer. So we call setup accelerometer, which is another function. And in this function, we, use device tree to get the label and then get the, binding for it to get the sensor so that we can actually use that to run other device related functions. And, it's not here for the ADXL 345, but you may desire also to set up the sampling rate, for example, for the FXOS 700 or whatever, you would want to set the sampling rate pretty high. So you would use a different API that Zephyr provides to set the sampling rate. Instead of doing this all yourself, you can use the Zephyr APIs to make this process a lot easier, provided, of course, that Zephyr has a driver for the sensor that you want to use. So that's what you do in the setup of your hardware. But let's go back to the main functions of the Hello World. So we've performed out the setup. We've set up everything that TensorFlow needs, and we've also set up any applicable hardware, which in the case of this example is none. So now we're going to kind of take a little brief walkthrough, not too much detail as to what they actually do in the loop. The key features here is that you need to get the input somehow. Here, they're just calculating the X values. So there's 0 to 20 cycles, right? So they approximate pi and some 0 to pi, and they want to get values along that interval. So if it's the first cycle, we want to get 0. If it's the last cycle, we have 2 pi. So we're calculating sine values along that. It just loops back, right? So that's the way they did it here. But of course, when you're actually using TensorFlow Lite Micro, you'll want to read out of some kind of sensor and put it into the input data. You see here, it's pretty simple. We just use the first one float and put in that X value. For an accelerometer, you'll want to put in, multiple, things. For example, in the magic wand, you can see here. Okay, well, you can't see here because I can't find it, but so read accelerometer. Now see what I did there? That is the power of CMake extension. So install it for your Visual Studio Code. Oh, maybe not so powerful because it didn't actually take me to the actual function. All right. So this is all reading data out of the sensor. This is our sensor channel get, and it gets the X, Y, and Z acceleration and it puts it into Excel, this buffer here. So we read it out, put it into this different array, which they use, and then they copy this X, Y, and Z array, they copy it into the buffer for the input because the input is a single array. They copy the X, Y, and Z as the first, second, and third values repeating. So that's another example of what you might do to, for example, take data out of the accelerometer and put it into the input tensor, which again, like I mentioned, is being used by TensorFlow. So let's go back to main functions. So put it in, run the inference, report any error that you want if it failed to invoke. And then once you've run the inference and it's successfully completed, read it out of the output. So I already talked about what the output is. It's just a single integer, which is the Y value. So once you have that read out, you can come up with your own custom error handler or output handler to output the result. So in the case, it's whatever's printing this. I won't show you that, but it's just printing, it's taking those float values and printing it out in this readable format. And then, of course, repeat your inference. So those are the basic key components, kind of generic, illustrated through the Hello World example of what you need. So now that I've talked about Hello World and also a little bit about the magic wand, I will demonstrate the magic wand sample very quickly, and then we will finish up this talk so we can have a little bit of time for questions and comments and any suggestions. So for the case of a magic wand, give me a second. Moment. Okay. See, I already have a build here. Get rid of that. You can see in the magic wand README that you need to, if you want to run it with Renode emulation, and by the way, Renode is kind of like the Docker of embedded. Basically, they can emulate boards, which makes it easier to develop your boards without actually having to hook them up to things. And you have a pipeline basically. They're going to have another talk about using TensorFlow and Renode, which I believe they were kind of sponsored and they collaborated with Google on that work. So I think that's tomorrow and you should definitely attend. It'll be great. So basically you need to, this is the wrong README, I'm sorry. Hold on. Just build it for the Litex board, which is the board that we'll be emulating. And all the Renode setup is here in this Renode folder. And you can go look more into their APIs if you're very interested in Renode. Oops, I always forget that. So that's the board. Just build it. Oh my gosh, I misspelled the board. I do this all the time. Okay, awesome. Just build it. And it thought it finished really fast, even though I think I deleted the build folder. It is done. So now, instead of running it with Zephyr, you use Renode, and you need to install this. It's a little bit of a process, and it has a lot of packages, but it's very cool. And this command here, you can see, it's Renode, executable, you call it, and you give it this kind of script to run. It sets this variable Zephyr elf to the build Zephyr elf, which, the elf in the folder. And it kind of tells it to run this script, which is the resc. You can see here that this script loads that binary, and then it gives it the data in the sample. So first it gives it the circle, then it gives it the angle, then the circle again, and etc. So you can see how this would be really useful for testing. Now I won't maybe not chill, but I won't promote it too hard because of course they'll give you all the fantastical updated details tomorrow. But yes, that's how that works. So you can see here's the data. I think this is actually borrowed from the training data that you could download for this app from TensorFlow. But yeah, so that's the data. Now we'll run it. Actually, probably should have started running this while I was talking to you because it takes a little while to do it for whatever reason. So in a moment, it'll run and it will get the first one. So give it a second. Don't worry about these. Come on. You can see there it is. It recognized the ring. So of course we're feeding it this pre-set up data, but it is using. Oh, I forgot to show you. I forgot to show y'all the model. Hold on. I said it was a C array. So here's the model. It's only like how long? Let me look. It's only like this many integers long. So that's pretty small. You can see very small. That whole model has been compressed into this data and it just gets loaded and executed. So that is really fantastic. Okay, we are now approaching, I think, 20 minutes left of time. So I'll let this thing continue to run in the background and I will continue my presentation. Oh, sorry. Let's wait a minute, let's try presenter view. Awesome. Full screen this for you. We'll get to the conclusion of this presentation. My tips for application developers, in addition to the basic outline of a TensorFlow Lite Micro app that I described to you, please make sure that your code does not use C++ features that are not supported by Zephyr. This includes exceptions, dynamic object management with new and delete, real-time type information, and static global object destruction. So as a side note, our support for exceptions is currently a work in progress. So we are trying to enable it. It works on a couple of platforms already for some reason, but it is currently being enabled. People don't usually use C++ exceptions, so for embedded, that's why we have not have not implemented it up until now. But there seems to be some interest. These features are not used by the TensorFlow Lite Micro library, but you may have some desire to use them in your app, in which case I say either don't or help us implement these features. So it is also a good idea to check to see if the board that you select is supported. You can follow that link to see the list of all boards supported by Zephyr on the Zephyr website. Another thing that I think you should do is check to see if the sensor you want to pick has drivers in Zephyr. This may make your life a little bit easier. You won't have to incorporate the vendor supplied drivers into your project or, write your own driver, God forbid. Yeah, and if you follow that link, it will take you to the drivers/sensor folder, and you can see all the wonderful sensors that we support, which there's a lot of them. Every time I open that folder, I get lost in Visual Studio Code. I would also encourage you to model your application off the TensorFlow Hello World sample and to ask for help on Slack or the mailing list if you get lost. So I'm on Slack primarily, but there's a lot of smart people on the mailing list too. So yeah, and file bugs or enhancements you'd like in GitHub and tag me so that I can see them. So that is my tips for the application developers. And my plea for contributors, please contribute. Please, I would love that. I will love you forever if you contribute. So we're looking for TensorFlow users, looking for people who want to use TensorFlow Lite Micro, and people especially who want to use them on Windows and Mac. Because as far as Windows and Mac goes, overall, a lot of us developers are working on Linux. I personally am working on Ubuntu 18. So we don't often get a chance to, put these products trial by fire. We have great Windows support. We have Mac support. But in terms of TensorFlow as a new feature, we want to make sure that the Windows and Mac users are getting, what they're owed. So please, give us the feedback or help us out. Contribute bug fixes, enhancements, samples, K-config options. We only have one right now. This could be you. You could be in here. Wouldn't that be great? You could add your company to this copyright. That would be fantastic. So yeah, if you want more information about the TensorFlow module, you can check out the request for comment PR that was approved by the TSC, Technical Steering Committee, I guess that's for y'all who don't know, that added the initial module support and see the discussion in there. And you can also check out the TensorFlow module repository. It may be changing in the next month because, like I may have mentioned, I just found out this month that TensorFlow has decided to refactor their entire repository to move TensorFlow Lite Micro into a separate repository. So that is coming. You can also read the documentation on Zephyr modules. So those are my tips for contributors and my desperate plea. Not desperate maybe, but it'd be great if you could help out. And yeah, so again, like I said, TensorFlow as a Zephyr module is very new. And we really want your support and your questions, your comments, suggestions, etc. So yeah, let me just give me a second to check the chat really quick. See if someone's here. Yeah, it looks like probably is not here. He gave me the suggestion that he wanted a K-config option, which we have. We are also going to be thinking about how to calculate the footprint of TensorFlow because I know it's pretty resource intensive, even micro. But besides that, do you guys have any questions? Do you have any comments? Do you have suggestions? This time, the 7 minutes, sorry, I meant to give you more time. At the end of this talk is for y'all. And if you think of anything after the talk, I am on GitHub and Zephyr Slack. I guess you can't message me on GitHub, but you can definitely message me on Zephyr Slack. My name is also incredibly generic, so you could probably guess my Intel email if you have a desire to email me. So yeah, okay, go ahead. If anyone has any questions, feel free to put them in the chat or to come off mute and say something.
Hey, Lauren, really great talk. Thank you so much. I was curious if you've tested this on any real hardware, like a physical accelerometer.
I am currently in the process of putting this onto the Freedom K64F board. It seems that there is some problem with the driver where it is rejecting me trying to set the sampling rate. So that's still a work in progress, but hopefully when we get that to work, we'll have it on the Freedom as well as the Renode, which I don't know, maybe Anas will want to remove the Renode, but I think it might be a good idea to keep it in there. But the Freedom board is the candidate for hardware support. I was hoping to have it for this demo, but unfortunately not.
Awesome. Well, I'm the maintainer for that sensor driver, so reach out to me later and we can figure it out.
Okay, sounds great. Yeah. All right, well, if anyone else has questions, feel free to stick around, but if you don't, go get a coffee, get ready for the next presentation. There's going to be a lot of fun presentations this summit, so get what you paid for. I guess you didn't pay for a ticket, but get what you signed up for. Gave us your emails, I think you gave us your name, so get what you paid for. So yeah.
Thanks again, Lauren. Thanks everyone for attending. I think this is our last talk for today, but we'll start up back again tomorrow, same place, same time.
Oh, okay.